So I guess we are live.
Yes.
Are we live, Laura?
Yes, I'm guessing we're live.
Okay, great.
I'm hearing myself twice. Let me just mute this here. Okay. So, do you guys hear us? I'm guessing we're still with the we're not showing up.
Yes, we should show up right now.
Great.
So okay. Can you confirm if the screen size is okay and if you can everyone can see us and listen to us?
Let me double check here. I can watch it and it's okay on my phone as well. So perfect.
Great. So welcome everyone to our second live on embedding. So as you already know, and we also know and digging up a lot more. So embedding is a huge topic. Lots of things to discuss, show. So this is our second live on embeddings. Maybe we'll have more. I don't know. But the main focus today is first to talk a little bit more from a more practical perspective on embeddings, what they're made of, how can you generate your own embeddings, how can you visualize them, and see if they're correct, and some other important things about them, right?
Perfect. And can you guys just confirm us that you can okay. Fran says that we have an echo.
Okay. And now?
What about now, Fran? Or anyone else? So guys, tell us where are you listening us from, and can you hear us well? Perfect. So here we go.
Got fixed? Yes, great. Okay. Remember to always mute the microphone on Xbit, right? Okay.
You know technology.
yeah, IT stuff, So let's get right into it, right, Laura? So just before, let me introduce myself again. So my name is Dionisio. I'm the co-founder and CEO of J. Here with me is Laura.
My name is Laura. I'm a data scientist and one of the co-founders of J. I'm guessing you guys are used to seeing us by now. And if not, please check our list of videos and previous lives, and then you'll get used to it.
Yeah. Remember to follow us on social as well. So we love your feedback. We've been improving on top of your feedback and choosing the topics that we are discussing in our lives. So we're really happy to have you here. And we hope to provide as much value as possible so that you can keep coming, keep asking us questions, and we can thrive together and use the machine and don't let the machine use us, right? So
yes, for sure. And if you guys want to ask any questions, you can put on the comments. I'll be checking this regularly. Also, if you are seeing this video after the live passed, you can also put your comments or questions down below. We'll be checking them, or in either of our social media. So our social media is they're all linked down below as well in the description, and you have access. If you already have your J key, you will probably want to go to our Slack community, but all the other social media links are also in the description.
Great. So okay, let's go right into it, right? So what are embeddings? So the classic definitions, if you just Google what are embeddings in the context, of course, of machine learning and deep learning, embeddings are low dimensional representations of data as continuous vectors. So Okay, what does it really means? So it means that you have data, you have raw data like an image and text, a table, or really any kind of data like audio data. And as we already know, you can't just feed this kind of raw pixels or raw text data into algorithms, right? You know, algorithms are based on math and matrix multiplications and things like that. So we really need numbers to represent your raw data. So you can use raw pixel intensity values to represent your cute cat picture. But as you already might notice, it is quite high dimensional, right? So imagine how many pixels and how many different channels you have for representing this picture. So it's not an efficient way of representing your data. And the same goes for words. So you can use something, we'll see, you can use something like fixed embeddings to represent your words. And to feed in your algorithms, but the thing is, how can you best represent your data? So that's why we call the vector representation. So we really are talking how can we transform this cute little cat in a vector. This curious product review text also from the raw data into a vector. This guy accidentally ordered a fry pan that was too small, or even structured data, tabular data. How can you transform it into vectors? So the thing here is that maybe we should just briefly answer why, right? So why are we bothering to do this? So embedding, ideally, it captures semantics of their data, right? So you not only are kind of compressing your data into this lower dimension, but you're also extracting semantics in a way that when you take a look into this embedding space, you can see similar things close together and not similar things further away from each other. So we have here's some examples for words. These are the more frequent that you see on the internet a lot, which is the word to vec. So you are mapping words into vectors and then you are plotting them into space, and then you can see similar words close together, and you can also do what is called like word math, right? So king is related to queen, as man is related to women and things like that. And on the right side, we also have those similar pictures. So if you're embedding words, you get similar words together. If you're embedding pictures, you're getting similar pictures together. So imagine this in the context of e-commerce recommendations, fashion recommendations, or even like image search and documents retrieval. So you're really looking to search for similar things.
Exactly. And also imagine this in a more complex environment. So here he's showing examples with just one word or just one image, but you can have that cat in light or dark. You can have that cat turned. You can have just one word, or you can have a sentence. And if you put a no before a word, then maybe the sentence meaning has a shift and completely changes. So this is a very simple example, but this can escalate really quickly, especially when we are talking about structured data. Okay.
Yeah. So and the first thing that is worth mentioning, and it's not really clear at first when you start studying and understanding embeddings, is that there are two kinds of embedding. So nowadays you more often see the learned embeddings things, which comes from the natural language processing models, the vision models, but in reality embeddings could also be processed. So when you have standard things like one-hot encoding, right? When you get you have your categories and you're transforming them into, you're just putting zeros and then one on the category itself and splitting them into rows. In reality, what you're doing is generating a representation of something that wasn't a number, right? You're creating a representation of that raw data. So one hot encoding and these other vectorizers, these other functions from scikit-learn, they're all generating embeddings to represent raw data, but that's what we call the processed embedding. So there is a processing to generate them, but they aren't learned. You aren't learning them inside a specific task, which contrasts with the learned embeddings, like the now more widely known BERT, GPT, and other NLP models that you can easily access through like Hugging Face or other model hub, model repo, which are pre-trained models, and that's the main thing here. They went with large, massive amounts of data to train those models with a task like predicting a word in a sentence. So during the training phase, they randomly, like Google or OpenAI, they randomly hided some words, and the model had to learn to predict the missing word. And this kind of pre-training task made the whole big network to understand the semantics between words. So after it was trained on this task, you can now just, and we'll show it, you can just feed it with new strings, new words or sentence, and getting into the other in the output a representation based on what that network have learned. So that's the main difference. So for instance, when you have this kind of processed vectorizer or embedding generation based on scikit-learn. So this is very common one. It's called the count vectorizer. So what we're really doing here is counting how many times each word appears, right? So we have different sentence, and our latent vector here is just the size of our vocabulary, and the number that appears is the frequency, how many times that word appeared in that sentence. So you can see that the first word of the vector, for instance, is and the word and doesn't appear in the first sentence, it doesn't appear in the second sentence, but it appears in the third one. So that's why we have a 1 in the third vector and on the first position and not on the other one. So we are, again, starting from raw data and transforming them into vectors, into numbers that can be further processed by a logistic regression, a gradient boosting, or a neural network.
You're gonna realize that we're not going through the same steps that we. This is the second live, so if you're missing any important point, you can go back to the first one, or you can either ask your question here. But just in a little bit of context is that we need to transform this into numbers, and we need to choose how to do this, because machines only understand numbers, and the way you choose how to represent your data, specifically and especially your categorical data or image data, and in this case sentence data, you have to decide in which way you are going to pass this to the machine, and the machine has to be able to understand that. So this whole process, this whole pre-processing and deciding if you're going to use a static vector or a learned one, this will have an impact on how your machine is going to learn with your data, because this will have an impact on how the machine is going to understand your data. So that's the big why here.
Yeah, totally. Yeah, you really wanna not only wanna you want to extract semantics, but that's because you want to do something, right? That, as Laura said. So you want to either search for something and similar things, or you want to make a prediction, make a classification, and that's why you want to extract the best of your hard-earned and treated data. And the thing here is, look, it doesn't matter what I'm doing after this. I'm feeding my algorithm the vectors, so we can in what we call the downstream task. So if I'm doing a classification, or if I'm doing like a sentiment analysis, if this tweet is positive, if this tweet is negative, we're just feeding this generated vectors through them and using them as features. On the other side, so this is an example of processed embeddings. You could use other methods that we described it in the previous slide, and this is, for comparison, this is a learn embedding. So here we are using the transformers pipeline from Hugging Face to extract the feature data, the vector representation from some text data. But we are using the pre-trained, in this case it is the Distill Roberta. So that's it's a whole NLP model, which was like I said, pre-trained on those huge large corpus and learn the semantics of different words. And now we don't need that huge data set, we don't need anything, we just need to use this pre-trained model to extract semantics and extract a meaningful vector from it by passing our raw data through it. So it's nowadays we can do it quite easily by using feature extraction pipeline like this.
Exactly.
And as you can notice, so the feature vectors that comes from the learned pre-trained model are much bigger and really dense representations. That's what we call the continuous vector in the I guess in the second slide of this presentation. So you really have this dense vector that we extracted from the neural network. And as you may notice, so you have what we call embedding size. So when you are passing data through a method or a model and just extract a vector in the other side, a vector has different dimensions, and that's something that we usually have to choose. So if we are doing what we call the categorical embedding, so if we are feeding categorical data through neural network, we can choose the vector size, the embedding size that we are going to use to represent our data inside our network. We can go deep into details, maybe in another live, but there are two rules of thumb for choosing this the embedding size in this case. So basically, you can take the log of the cardinality. The cardinality means the number of unique categories or data that you have in that feature column, or you can take the square root of the square root. So it's the fourth square root of the cardinality again, so that you end up with this kind of heuristics of how much bigger it can be or smaller, right, Laura?
Exactly. And also keep in mind that this is one of the main reasons that people say you have to have huge data to run a deep learning, and you have to choose all of these details. And we promised on the last live that we were going to do another one about pre-trained models, and we are going to, but you asked for us the embedding is part 2, so here we are. But next one we're going to do about pre-trained models, and this is one of the reasons why we can we can use a pre-trained one and not without having to worry about all these minors, not minor, but these other steps. You don't have to have this thing in mind. One thing we always advocate is that data scientists already have a lot of works, right? Especially if you are in a small company and you don't have that architecture in which you have separate roles and you have one person or a small group of data scientists that actually has to do everything from data collection, ensuring data quality, and also going all the way into production. So not having to worry about how you're going to do your categorical embeddings, and if you have enough data and cleaned enough data to work with deep learning, I think it's a kind of a blessing, right? You can choose a pre-trained model and you can use J and you can use something that it's built for what you have, and you don't have to worry about this. You only have to worry about all the million stuff that you already have on your plate.
Yeah. One thing I think is important to notice is that if you are using pre-trained models, like Laura said, so if you're using BERT for natural language processing, or if you're using ResNet or things like that, so as we said, so you already have a model, right? You already have a pre-trained model. So basically what we're doing is extracting the feature vector that comes in the middle of that model. So the vector dimension is already defined by the model. So for instance, if you're running your data through BERT, it already has 768 dimensions. You can further process it to change this dimension, but the feature vector, as is extracted from the model, has a fixed pre-established dimension by the architecture. You're really not having to deal with that, right?
Exactly.
But if you are training your own model from scratch and you want to extract your own embeddings, well, that depends on, I know this is quite vague, I'm sorry, but that's the truth, right? It really depends on the model architecture and the task. So the thing that we're doing is you're creating your model and you're running data through it and just checking both the model performance and taking a look at the embeddings, which is one of the topics that we're going to talk about. But we're really trying, you need to try to diagnose whether you really have meaningful and good embeddings or not. You're from your own model from scratch, right? Your own, you created your own architecture and you're using it.
Sure. And if you're building your own model from scratch, well, first, I have my best thoughts with you. Good luck. And second,
Yeah.
I hope you have enough GPU and time, and I hope it all goes well. And we are going with the pre-trained giant so far because we chose that. Nothing against training it from scratch, but again, I hope your sanity is checked up.
Yes. Yes. And then like we said, so if you want to diagnose your embedding, so let's say you just ran through this learning embeddings from transformers pipeline, from Hugging Face, or you've created your embeddings from J, and you can check how can we do that in other lives. So we're not focusing on just J right now, but you can easily generate your embeddings, use pre-trained or your own models with J. But the thing is, we can't really see more than 3 dimensions, right? So the first thing that you need to do, if you want to visualize your data and you want to try to understand what's going on, you really need to reduce the dimensionality. So there are 4 main algorithms to do that. So the first one is PCA, but PCA is linear. so it's not really recommended to use PCA as it's a linear decomposition. With such nonlinear data from neural networks, you probably should use something nonlinear as well, such as UMAP or TSNE, or more recently the MDE, which stands for minimum distortion embedding. So those are three like classic ways of reducing the dimensionality of your data back to something that you can actually see, you can actually visualize, right, Laura?
Exactly. And this is important because, first we wish the world would be more linear or more in a normal distribution, but it tends to not do that. It has fat tails, it has messy data, it has a lot of things. So you probably want to go with one of the nonlinear libraries. And why are we calling this slide diagnosis? Because think that you have a vector that is ready for machine consumption. So if it's ready for the machine, it's not ready for humans. And if it's not ready for humans, how do you check if they have meaning, if they're meaningful, if they actually are able to pass through the machine what you want? So, and what do you want? You want the best possible representation of your data, so the machine can learn with it the patterns, and then produce a model on top of it. So one way to diagnose this is, well, let's see. Let me open this black box and see what's inside. And since vectors usually have high dimensionality, that's why we have to reduce it first and then plot and visualize.
Yeah, so and to really plot them, you can either go with standard pyplot, matplotlib, and just do your standard scatter plot really, and see how the dots are clustered and things like that. Mm-hmm. Which we will also provide you, but I mean it's really quite standard code to do it, but we'll provide you with a notebook to do that. Or you can use a very nice tool available by the TensorFlow team, but the TensorBoard team, which is called the TensorBoard Projector. So it's an online tool that we can navigate and interact with the vector clouds to see the meaning of them. So let's check it out, right?
Yes, and we are going with TensorBoard now because in previous lives we already showed the other plotting with pyplot and also with Seaborn. So you can check it out. If you want the notebooks, you can go to our Slack community. They are all in there. Or you can ask us for a code snippet or something. Not a problem. But we have an extra about TensorBoard that is... it's cool because we can see in 3D and we can interact with it. So let's check it out.
Yeah, just let me change it here. Just a second. And while I change it, maybe it's important to note to say that what we are really looking into. So it should be this one, I guess. So can we see it?
Yes. Okay. I guess we are...
Yeah. I'm fixing.
Okay.
I'm trying to fix it.
Not a problem.
It should be better now.
Okay. Okay, it is better.
Great.
Guys, can you see this? I'm checking on my phone as well, but for me it's okay. Is everything okay for you? Oh, that's better. That's better.
Yeah. Probably, yeah. So what this is the default vector cloud from the TensorBoard. This is the word to vec. So basically every point here in this this is the vector space. So we are looking at words that were turned into vectors, and they were projected and plotted in this 3D space. It could be either 3D or 2D. So we were looking at the PCA, and now we're doing the nonlinear dimensionality reduction, so we can visualize it better as embedding the word space. So which words are close to each other in this word space, and just let it run for a while. And I think this visualization is quite interesting, because it really comes to the point where we say, oh, the embedding space, and it really is a space. Like, things have distance from each other, right? Words have distance from each other. Images can have a distance from each other. Table, rows, every piece of data, when projected into their own embedding space, they start having neighbors, and this is what makes it fascinating and quite useful in practice, right? I don't know if I'm getting too excited with this word vector, and it's super nice.
By all means, and it is very nice. But for those who doesn't understand embeddingness, well, what are we looking here? So why are these points dancing and floating? So what happened here, right? So he just switched from the PCA to the TSNE, and as Dionisio mentioned before, this is for the dimensionality reduction. And the way you reduce this dimensionality, so we can see, because the machine can deal with 128 dimensions, but we can't. We can tops go to 3D, all right? So we have to reduce this dimensionality so we can see this. And the way you reduce this dimensionality matters. And another way of checking that, and if you realize, when he switched from one way to reducing to the other, it showed on the screen something written, calculating the neighbors and everything. So that's what he meant about distance from vectors in the vectorial space. So what does it mean? So if you have like your 3D, then you have the distances, like the graphs that Dionisio showed before. And in that case, he showed that queen and king are closer to each other in a similar way as men and women in that example, in that specific example. But in this case, what kind of data are we looking at?
It's the same thing. So it's exactly what we were saying. Oh. So like bread is next to wine, it's next to meal, sauce, fried. So naturally, all these words. So and sorry if I went a bit too quickly on that. So we have 10,000 words, which were mapped through the algorithm word2vec into a 200-dimensional vector. So each word became a vector with 200 numbers, 200 dimensions. And then, because we can't visualize 200 dimensions, unfortunately, we had to use an algorithm to reduce it to something that we can then see, which is 3 dimensions. And then for that, we use TSNE, which is a quite standard way of transforming high-dimensional data into low-dimensional data that we can visualize, but preserving the neighbor structure. And the thing about diagnosing if this is, okay, I transformed the word wine into, or the word bread into a 200-dimension vector. Was it worth it, the trouble? So here we can, so we plot the data and we inspect their neighbors. So if we did a good job on translating and making this word into a vector, if we did a good job on it, then when we take a look at who is closer, who is really next, who is neighbor of this word, the other words, they should carry some meaning to us. So in this case, we are really looking into similar concepts or similar words or things that probably should occur together in sentences or in the same context. So when we click in, we selected bread. So we now have here in the tool itself, we can check that it's wine, it's bread, so wine is really next to it, meal, sauce, fried vegetables, so it's food concepts that are close together in this word space, right?
Yes, and this is so important that in this case, we are talking about meaning, and the way you extract your embeddings and the way what you want your machine to learn about your data is crucial here. In this case, the pre-trained model, the word2vec that is famous for it, is designed to extract the meaning of words. And another thing you can do is, for example, for an image, you can just extract the shape of an image, or maybe what's written in the image is more important for you, and then you have to have a model that has an OCR together. Or maybe it's not words, it's a whole sentence, but you also have to have meaning. And in which language is that? So Bert and the Hugging Face solved that for us, thank God. And now these are the most common examples. And what if I want to do that with my structured data? So if I have a time series problem, what do I want the machine to learn here in the vectorial space that will represent the best my data, that the machine can learn from it and build a model on top of it? So that's the way of thinking with this. So this is an example. And why do we call this diagnosis? Because if bread is closer to, I don't know, broomstick, and further and more further apart than, I don't know, cheese or maybe whole wheat bread, then something's wrong. It's not what you would expect. The other example we showed in the previous live is that if you have a shirt and if you have a model that captures the shape of that shirt, you're gonna have similar shirts there, but it should be further apart from a pair of pants, for example. But if you want to take the color, then similar colored products would be closer together than different colors. So what do I mean by that? After you choose how to build your embeddings and you took them, you reduce the dimensionality and then you plot. You have to check if what you're seeing on your plot have any sense with the data that you passed, and if it has any sense with what you want the machine to learn from your data. So if you are trying to make a model that learns how to, for example, mimic a store that it's your best store and you want to open a similar one, and then you check your embeddings and see if similar stores, success stores, are close together or if they're further apart. So if these embeddings are meaningful, the clusters you want have to start building, and also you have to see similar things closer to each other. Does it make sense? Is it clear?
Yeah, and we can like carry this semantics concept further away, right, Laura? I mean, we are talking similar items, similar words like food, bread and cheese, but semantics itself could be something like similar customers that are willing to churn. So or customers that we can upsell or cross-sell. So they will be embedded in the customer space, and similar customers according to their behavior would be clustered together in the space. So you couldn't expect it. You could like perform search and use them as features for your churn classification model and things like that.
And this is one of the main reasons why recommender systems take huge advantage of this kind of embeddings, because I don't know, maybe if you are doing a customer recommendation of some products, right? You can check if this customer is similar to that one to offer the same thing or not. Or also you can do it in a simpler way. You can just see if you have a lipstick that is out of stock and suggest a similar product. So recommender systems can take huge benefit from this, and we would have a lot less errors than we see. Who never tried to buy flowers and then the app suggested, in case you missed this, we don't have this product, so instead of your flowers, you can take bell peppers. Have you seen this one? This one is so good. And we also have the one, I guess it was with you, right, Dionisio, that you went to buy meat and it offered you soap instead.
Soap, yeah, you can substitute. Yes, it was like, yeah.
So that when you use embeddings, if soap is close together with meat, your embeddings are not meaningful, right? So that's another way of building recommender systems using these techniques that we are showing right now.
Yeah. And just for another example, I just uploaded in the projector another data set, which is quite common. It's called the US Census data set. We've been exploring it in our previous lives, doing classification, self-supervised learning, and things like that. You should really go check it out. But right now, I just uploaded. We have applied self-supervised learning to the US Census dataset, which is the standard one from Kaggle, I guess. And then, as we said, we just transformed each entry in the table, each row, into a 128 dimension vector, and then we are plotting here. So if we really want to understand, okay, did it work out? So I'll just change the label to income, and okay, so it's kind of psychedelic, but we'll figure it out. So first things that we want to know is, do neighbors look alike, right? So if I get a point here, and we have a list here in the right of their work class. So what do? So they all have the same work class. If we change it to occupation, let me change. Okay, so again, people with similar occupation appears to be neighbors of each other, right? So each point now is a person from the US Census dataset, which has several attributes such as work class, education, marital status, relationship, race, sex, native country, and things like that. So when we start inspecting our embeddings, we really wanna that similar people are clustered together in this people space, US Census people space right here. So, and it works, right? So we've applied self-supervised learning with J to extract those vectors, and you can see it works. So 128 dimensions can map really similar people next to each other, according to several attributes at the same time. But much and more than that, the main thing about this data set is to classify, to predict whether someone, given their attributes, has an income greater or lesser than 50K. And when we just let me okay. So what we did here is to color those points red if they are. Let me get this into 2D actually. maybe it's easier for us to visualize. So red is they earn more than 50K, blue is they earn less than 50K. So if this turn the tabular data into something useful for a classifier, we would expect to have a data that a further classification algorithm can draw a decision boundary, and then we know that this will be a good feature to feed a downstream classification test for it. So I'll stop the mayhem right now.
And it's also so pretty to see, right? I'm enjoying this. Are you guys enjoying this? Let us know later on.
Oddly satisfying.
Very pretty.
Yeah, it's oddly satisfying to see this kind of thing moving around. So of course you can see it's not perfect, and we're doing, from 128 dimensions back to 2 in this case. So you kind of lost, you kind of lose something in between. But as we can see, we have a concentrated mass of red dots and a concentrated mass of blue dots. So we can understand that this embedding not only got similar people together, but it is also meaningful to classify this label, the label of the income of each one. So it's a very practical way to diagnose if your embedding makes sense, if it is doing what you're supposed to do, if it's gonna be useful for something.
And that's a way of debugging your deep learning model as well. So if your error is too high, maybe you want to check your embeddings. Yeah, that's a good start point. And also, just going for a close-up because of our time, we have now a new way of checking if your embeddings are meaningful or not. You can also go and do a j.similar, and then you just print your table and see if it makes sense what you're looking at. So that's one of, I'm not going deep on this because we have several lives all about J. This one is not one of these. But that is one of the main reasons why in every live we print our J-similar and see if it makes sense, if it stores that are supposed to be similar, if they're close together or not, if the Boston housings that are supposed to be similar, if they're close together or not, just to check if our training was done well, if our embeddings are well, and then we go to the next step. So this is critical. And when you check by similarity, I think it's a good deal for structured data because you can see all the columns. So you can, of course, do and check your embeddings, visualizing them with a graph. But when you print the similars, I don't know, the top 5 or the top 10 similar, you can go column by column and see, well, these make sense. They are closer together and they have most of the columns of the same or very similar to each other. And also, my departments make sense as well. So my furniture items are closer to each other compared to my, I don't know, Bed Bath and Beyond, something like that.
So that's our thing, right, Laura? Doing basically similarity search, looking for the neighbors, using vectors to fit things that to feed downstream models. That's the J way of doing things. I guess are you guys still listening to me? Maybe Laura froze up. I don't know. Maybe I just froze up. But I mean, so this is when we click and point, this is exactly what a J-similar would do, and to use this as a feature, we would just draw a classifying line here, a frontier from a downstream algorithm. I still don't know if just Laura froze or if I have an internet connection problem myself. Just let me. Oh, probably she got a problem. Yes. Okay. So. Okay. So, anyways, thanks everyone for coming. And this was our part 2 of Embedding's presentation. Thank you very much. Please don't be shy. Write your feedbacks, your comments. We'll try our best to answer them. Join our Slack channel. Thank you all very much, and we see you in the next one. Thanks.